introduction to the field, which is a daunting task because the field spans so many different experimental platforms and ideas. But I tried to give a very short overview of what we hope to see, and certainly doesn't cover everything that we will see and enjoy during this 3 days. For me, this workshop is an incredible pleasure because I feel like this is home. This is my community. Everyone here is interested in the same things that I'm interested in, and that's a very unusual thing in Cavity QED and many-body Cavity QED. We're kind of a niche group in the wider world of AMO and many-body physics. So I really look forward to doing this with you, doing this meeting. Okay, so back to the quick introduction. So this workshop's on many-body Cavity QED, and so a lot of this will be colored by my personal views. It will completely be covered by my personal views on this field, and I hope to be enriched by your views. From my perspective, I see this as a new tool for studying organization of matter, in particular non-equilibrium quantum matter, where there are aspects of those kinds of systems that we don't already understand in some other contexts, like in solid-state physics. So from my biased perspective, this is the canonical Cavity QED system, where you have some nonlinear matter confined between two mirrors that support an electromagnetic mode, or many modes, and those two can interact, can exchange quanta of excitation, and that interaction can be pristinely studied either from the atomic direction or from the photonic direction. Now, of course, this has now been embedded into solid-state materials, but a lot of the ideas, I think, carry over. So there are many different types of cavities out there, starting from the Fabry-Perot cavity that we know and love. This is Jeff Kimball's famous cavity, where you can't even see the separation between the mirrors in order to confine to increase the energy density of a photon. But these sorts of systems have been extended to quite a wide range. So you have microdiscs, microtoroids, waveguides now that are being explored that have similar behaviors to cavities. Jakob, who just came into the back here, we can all be in first name basis here, it seems like, has pioneered these very, very small fiber cavities, which are extendable into many different scenarios with ions and so forth. Serge Roche has famously studied these sorts of systems in a different electromagnetic regime, in the microwave regime with Rydberg atoms. Yelena Vukovic and many others is just a placeholder for a wide community that studies photonic bandgap-like cavities that have a very different character than the Fabry-Perots. And of course, we have represented here and elsewhere a large number of people who have run with the idea of doing Cavity QED in circuits using superconducting systems. And there's many here, Cater's here, and Dave and others. So we'll hear a lot about these in the coming days. So what is an example of many-body physics that one can do with these? So in my mind, the first, or one of the first examples, is really this idea pioneered by Vladan Vuletic, Helmut Rich, and Peter Demolkos here, which is to take atoms in a cavity, many atoms that are initially disordered, pump energy into the system, and if you play your cards right, then the system will spontaneously organize into some state that breaks a symmetry. And here it's a Z2 symmetry, an Ising symmetry, into this checkerboard pattern. And this is a very interesting type of phase transition that really doesn't have a lot of other counterpart in AMO physics at the time. Now we see it in many other regions, but this was extended by many other authors and experimentalists and theorists to think about what is this phase transition, what does it mean from a quantum many-body physics perspective. Okay, so what does Cavity QED offer for many-body physics? We can maybe do it, but what can it teach us that we can't get from looking at a solid-state system? Well, we have strong interactions. So if you design your system right, the the particles, the constituents, can interact very strongly with one another so that and maybe in principle the quasi-particles of the system are non-trivial. And we can do that by cranking up the pump of the system. So it's intrinsically a non-equilibrium system, so we can crank up the pump. And you can do this to the point where this interaction energy scale surpasses the motional temperature of the system. And that's a nice feature because by contrast with isolated quantum systems, say in optical lattices, one of the big challenges is to reduce the entropy to the point where new phases can emerge. And that is an ever-going challenge of real precision experimental work that is very, very difficult to do to distill and not just get below, but get well below where the phase is well stabilized. In our systems, this energy scale is already at the very beginning can be orders of magnitude than the temperature scale. So you might say, well, okay, but there's dissipation. It's a non-equilibrium system. You have spontaneous emission. You have light leaking out of the cavity. But it turns out that not in all cases, but in many of these cases, the collective cooperativity of the system being greater than dissipation is what matters, and the collective cooperativity can be enhanced by putting more particles into the system. Okay, so you get this kind of free resource of coherence or cooperativity just by increasing the number of particles because you're interested in many-body physics. That doesn't always hold true. Sometimes if you want to prepare interesting non-classical states, then it's the single particle cooperativity that matters, but often for the many-body statistical type systems, it's the collective cooperativity that matters. Okay, so the system is intrinsically non-equilibrium, as I mentioned, which is a good thing in the sense that you have a ready source of information in real time. So when you're pumping the system, light is leaking out, and because you have this nice resonator, the light that is leaking out is in a well-defined electromagnetic mode in free space, which you can easily capture with detectors. And those detectors give you information about the system as you're going along. And that's a very hard thing to do in the solid state regime, where you have to perturb the system away from what you want to study in order to get a nice detection mode. So here we get that for free. The non-equilibrium aspect from the many-body physics can be both good and bad. It's bad in the sense that a lot of the intuition that you love and enjoy from understanding statistical mechanics, equilibrium quantum statistical mechanics, or classical statistical mechanics can lead you down the wrong path in this sort of system. The concepts just don't carry forth. They don't match. And so you might think that you're doing something and call it something, but it really is not that. On the other hand, that's really good, because the reason that happens is because we don't really understand all the aspects of non-equilibrium quantum statistical mechanics. And that is an unusual thing for us in the sense that there's some terra incognita in the physics. We don't understand some things at a fundamental level, and our experiments can inform that in a way that's hard to do in other areas of physics. And that's what's really exciting to me personally. Okay, so new frontiers in optical many-body physics. So here's where my bias is manifest. I won't be showing a lot of the wonderful circuit QED experiments that you've done. We'll wait for your talks on that. But let me just show you some examples of the frontiers that the people in this audience and elsewhere are exploring. So optomechanics. So Dan has pioneered a lot of these experiments where you look at few body systems moving towards the many body systems and how their motion relates with all the other motions. Maybe you get some sort of self-locking and some nice physics correlated between these oscillators. So as I mentioned earlier, Vladan, Helmut, and Peter Domokos, and many others have pioneered this notion of a structural phase transition concomitant with a superradiant phase transition, or in other words, a Dicke transition in these single mode cavities. And then others, like Andreas here, Hemmerich and Thomas Esslinger, has looked at this fact that you get long-range interactions in these cavities to get to have an interesting extension of the Bose-Hubbard model. It's called the extended Bose-Hubbard model and the type of physics therein. Many folks here at Harvard, John Simon and other people around the world have been looking at increasing the strength of interactions to go to new regimes where the interactions are so strong that you can get photon interactions mediated by the matter using Rydberg cavities. Rydberg polaritons. Monica Schleyer-Smith, who just entered at Stanford, is looking at also strong interactions, but by using tailored cavities, near concentric cavities, that have very, very small mode waves that can give you very high cooperativity and can give you very interesting structures for interactions. John here as well has thought about topology, non-trivial topology in cavity QED. So that's another exciting aspect of cavity QED. The Nobel Prize last year was won for non-trivial topologies in many-body physics. We can study that too, and this is a kind of Landau level physics or quantum Hall physics that can be studied. And when combined with these strong interactions from Rydberg, you can get some fractional quantum Hall, some non-trivial quantum Hall physics. Okay, and then there's been a lot of work on exotic condensation and crystallization in two-mode cavities where you can look at U1 symmetry breaking, Goldstone modes, and so forth, Higgs modes. Looking at condensation of photons, looking at crystallization 1D of atomic excitations, and in 2 and 3D, looking at kind of superfluid, stripy-like patterns in multimode cavities. I'll talk more about our own work in a moment. And lastly, you can look at the spin degree of freedom of the atoms in cavities. You know, with these 3-level atoms that Dan was alluding to, you can have a pseudospin 1/2 degree of freedom. And the pseudospin 1/2 degree of freedom can then be coupled to the cavity mode, and from the cavity mode build in interactions with the other spins inside the cavity to give you non-trivial spin models. And those spin models can now be engineered to be frustrated in multimode cavities, either in these kinds of engineered two-dimensional waveguide systems or multimode confocal cavities to give spin glass physics. And spin glass physics is proximal to neuromorphic computational systems that has another branch of exciting physics for us to study. So there's a wide plethora of phenomena that we can study in optical many-body cavity QED, and a lot of this carries over to solid-state circuit cavity QED as well. So I think it's a ripe community, a maturing community for us to focus on in the next few years. Okay, so now to jump a little bit more into my personal research. I'd like to focus on this example of the kind of the first motional phase transition of these systems and explain a little bit more about how this arises. So how can you generate atom-atom interactions or particle-particle interactions? So this is, if you're talking about many-body physics, you need to have interactions between the particles. So in this context, let me explain how this can happen via the photons. So in a single atom cavity system, you have an interaction G of x that's a coherent exchange of excitation from the atom, say the 2-level atom, and the photon field. The system can be pumped through the semi-transparent cavity mirrors to excite the system, and that can be exchanged at a rate G of x, where x denotes the fact that this interaction changes sign as a function of where one is in the standing wave or can vanish at a node. So on resonance, that's what the interaction Hamiltonian looks like. Off resonance, where one wants to operate to minimize spontaneous emission, in perturbation theory, one gets G of x squared over delta A. Okay, so by increasing the power, increasing delta A, one can isolate this interaction and have it be the largest, the fastest rate in the system. Now this is a kind of you can't change the sign of this interaction anymore because it's squared. So if you want to have sign changing interactions, then you can pump the atom system, this kind of the dual of the photon pump system. You can pump the matter first, and then in perturbation theory, you get this interaction scale where you have the pump strength comes in times the interaction to the first power. So now you can get a sign changing interaction, which is nice. So how do you build in 2-atom interaction? Well, in 2-atom interaction, to wave my hands a little bit, also in perturbation, you can think about there being a higher order process in which this particle here emits a photon into the cavity virtually at a time scale 1 over the lifetime of that photon inside the cavity, which is 1 over the delta C of that cavity detuning, where the pump is a little bit less than the cavity resonance, both of which are a lot further detuned from the excited state of the atom. You can borrow that photon, another particle can borrow that photon, coherently be excited with it, and vice versa before the photon is scattered in the forward direction. And so, in other words, you can take this interaction, square it, divide by the delta C energy scale, or multiply it by that virtual photon time scale, and get the interaction between exchanging virtual photons within the cavity, which then is, in other words, the way in which one can get an atom-atom interaction. And what's nice about this is now you have a sign-dependent, position-dependent interaction between the two particles. Okay, so let's look at that expression a little bit more. We can rewrite it in a more kind of cavity, in a more physical way, where we put all the atomic parameters over here. This is just the pump strength. And then we have these mode functions. These mode functions are simply the solutions to Maxwell's equation and these boundary conditions, where L and M in our notation is just the number of antinodes in the transverse plane, and the number along the cavity axis is 10,000 larger. Generally, you have a lot more wavelengths along this direction. Okay, so if this product here is positive, meaning that the particles are both in the odd or both in the even, no matter how near or how far they are from one another, then this is a positive interaction overall. With this negative sign, this becomes a very stabilizing interaction. The more they interact, the lower the energy. So it's a stable kind of situation. However, if the particles are only lambda over 2 or any multiple of lambda over 2 from one another, then this is negative, and this becomes energy maximizing, which is an unstable configuration. And that kind of situation can lead to the self-organization in the single mode cavity that I alluded to earlier. So let's imagine first that you have just a random distribution of atoms. If an atom happens to be at a node, let's say that it doesn't exist, and just put half of our atoms at the odd antinodes and half at the even. So initially, when you start to scatter photons from this regular array, you won't be able to scatter anything into the cavity, because for every atom scattering that photon at this position, you have one at exactly a multiple of lambda over 2, and that will destructively interfere. So you won't be able to scatter anything into the cavity. However, there are statistical fluctuations of the populations in the odd versus even, which will give you light coming out of the cavity. And if you have red detuned the pump so that the energy going out is larger than the energy going in, then eventually you can have this runaway process where you have a standing wave inside the cavity that emerges with the lambda periodicity, which then gives you a Bragg grating, where all the photons emitted into the cavity are in phase. And that gives you one superradiant emission proportional to the number of scatterers. This has been seen both in with thermal particles and also with BECs, where you get a spike of light coming out of the cavity, and then it decays as the atoms heat up due to heating processes like spontaneous emission. And if one looks at the atoms, then one would see a checkerboard pattern, okay, where you break the random distribution and you form a checkerboard of either the red or the black site. So that's a Z2 or Ising symmetry. And with the BEC, you can easily detect the existence of the checkerboard by looking at the Fourier transform, which is just time of flight. And the momentum peaks, these Bragg peaks, are evidence that you had this pattern with the distance showing that you have a checkerboard rather than every lattice site. Okay, so that's kind of neat, right? So this is unlike other optical lattices where every lattice site would be filled. This every other lattice site is filled. Okay, so what is this telling us from a many-body perspective? We have a discrete symmetry breaking phase transition. So unfortunately, that means that you have no phonons. If it's discrete, there's no rigidity to the system. There's no Goldstone modes. So if you wanted to use this as a quantum simulator for many other exotic systems that have that, you're kind of out of luck. And secondly, you have an infinite range interaction. So that's neat for some experimental models, some theoretical models that you might want to explore. But from the standpoint of many-body physics, it's a little bit limiting in the sense that a mean field description is always sufficient. Because since every particle is connected with every other, this is a complete graph. There's no room for inhomogeneities. There's no fluctuations in the system that can go beyond mean field approximations. So this led us to thinking with Sren Gopal Krishnan, who's in the audience here, of the need for multimode cavities to explore beyond mean field physics, where these fluctuations can matter and do something exotic, something surprising perhaps. Okay, so what does multimode cavity QED offer? So non-trivial topologies plus interactions can give you exotic states of matter. and this is what John Simon will talk about in a few days. It can give you dynamic synthetic gauge fields, plus interactions can give you interesting types of situations. For instance, the particles can organize in response to the light, but then they can cause the light to change and change that dynamic in a kind of a self-consistent fashion. And one can tune the interactions from infinite range to short range in a multimode cavity, and that's what we'll focus on mostly. And that, I'll just mention towards the end of the talk, can give you access to the simulation of quantum liquid crystals. These are states of matter that are found in many exotic, strongly correlated materials like pnictide and Coopered superconductors, or access to spin glasses, which are models for neuromorphic computation. Okay, so what is a multimode cavity? So it's in our language, and people use multimode for many different types of systems, but in our language, multimode means frequency degenerate modes of a cavity. So the simplest type of cavity like that is a concentric cavity, which is just a sphere with ink caps that are reflective. And so you can see from a semi-classical or classical viewpoint that these different K vectors, which are distinct modes, all have the same path length. If they have the same path length, they resonate at the same frequency. And so the larger the solid angle, the more modes that are degenerate. This is a kind of a hard cavity to build exactly. An easier one is a confocal cavity, which has a more exotic symmetry, but nonetheless, you can still have either all even modes or all odd modes degenerate. And this is an example of one we've built in our system, where you have, if you tune the length of the cavity to match the radius of curvature, you have a high density of modes. If you move it just ever so slightly away, then the mode family split out. You can get to a regime where you have nearly degenerate clumps of modes where the L and the M's are all the same, but they're separated from one another. If you were to move it even further, then even these would split up. Okay, so again, it's where all these transverse spatial patterns are different, but they all are at the same frequency. And that's interesting because when that atom emits a virtual photon into the cavity, it does so into all of these modes. There's no energy penalty to go into one mode versus another. Okay, so can you do this experimentally? Well, my students, many of whom are here, Alicia is here, Alicia Kohler is here in the audience. You can actually engineer this, which is quite surprising. It was surprising to me. I didn't tell her that it would be surprising, but it was really a tour de force, in my opinion, where you have a high finesse optical resonator, so something that's like 50,000 finesse that needs to be locked very, very carefully with a BEC that you want to put in, so it needs to be all UHV, so not many glues. But you want to have the top mirror to be able to go up and down by millimeters, so you can really, or tens of microns, hundreds of microns, so you can tune exactly to this degenerate condition, or away from it as you please. And of course, tuning something means that you're allowing vibrations into the system, and so you have to isolate that system from all the vibrations from people walking around or the building shaking. So we have a triple stage vibration isolation and can still get a BEC inside the cavity. Okay, so it works extremely well, shockingly well, I would say. All right, so the first thing we did with it is just to go somewhere between the fully multimode and the single mode regimes to the few mode regime, or basically the regime where you're isolating those degenerate families, and ask what happens there. And so here's one family. This is the L plus M equals 6 family. If you detune far enough away from the family, then these modes all kind of look like they're degenerate. Okay, if you detune close to them, then you can start to resolve them. And as you detune near far, what you get is some light that comes out of the cavity. So the red background is light coming out of the cavity. You get light coming out of the cavity that looks very neat, but not what you think of as textbook Hermit Gaussians. Okay, you get what Alicia has branded the turtle mode. Okay, so the next version of Sigmund will have this in there. So what is going on here? Well, what's going on is that as the atoms reach threshold, as you're pumping them hard enough so that they start to have a density wave, this kind of checkerboard density wave pattern, they're remixing they're a nonlinear element inside the cavity. They're like a piece of dielectric or a piece of glass that is mixing the modes of the cavity dispersively. Okay, that creates a new basis for the eigenstates of the cavity, which we call supermodes, those supermodes have a different spatial structure, which then back reacts onto the atomic positions in order to change the way in which they're organizing themselves. So you have the self-consistent back and forth of the organization as you increase the pump until suddenly you hit threshold for the organization, you get superradiant light coming out, your atoms organize into a density wave pattern into this new kind of self-consistent supermode pattern. Okay? So it's kind of a new way of thinking about how you have a polariton condensation. Here we call it, in this very unlovely phrase, a supermode density wave polariton condensate. It's a new type of non-equilibrium condensation phenomenon. It's analogous in some respects to an exciton-polariton condensate. The differences being that in these systems, the pump is near resonance, so you really have electronic excitations. The polaritons are very much electronic dominated. Here, you have dispersive pumping, where the excitations are really density wave rather than electronic. So that's the novelty of this system. Okay, so that's some flavor of what one can do. Another thing that we've thought about but haven't yet done, and this is in theory work with Jonathan Keeling at St. Andrews, is this dynamical gauge field or artificial gauge field. So what's an example of a very simple gauge field? A dynamical gauge field is simply that of the electromagnetic field giving you the Meissner effect in a superconductor, where a magnetic field is expelled. So we found that one can reproduce this kind of effect using a multimode cavity that has a dynamic structure of the modes that emerges. I won't go into the details of how you actually do this, but the idea is that if you have a BEC inside the cavity that's kind of in a disc shape, if you can artificially turn off the cavity back reaction, this self-consistency, then if you put a synthetic magnetic field onto the system through, say, Raman dressing, you would get vortices. But if you then turn on the back reaction, which is what the cavity actually does, this is just numerically, you turn it on and off. If you turn it back on, then you see that the atomic density concentrates around the center, expelling the vortices out to the wings. So it's the same kind of expelling of the magnetic field as manifested in the positions of the vortices. The optical intensity is mappable onto a magnetic field, and you see that the intensity or the magnetic field gets expelled, and that's the direct correlation between the two. So that's just kind of telling us that there's many types of dynamical gauge field type physics that one can do, and this is just the first version. Okay, so what do more modes give you? Well, they give you shorter range interaction. So here's a cartoon to explain how that works. So say you have several particles inside the cavity in a multimode cavity. You pump the system. Each particle is simultaneously coherently scattering that field. And so when, say, one of these particles scatters the field, it does so into the superposition of all the modes available at that energy, which can be hundreds of modes, thousands of modes. That's indexed by this alpha. And the interaction, as I explained earlier, is given by the product of this mode function at position 1 versus position 2. Now, because these mode functions are these Hermite Gaussians, and they form a complete basis for a delta function, the more and more that you have, the more and more these can constructively interfere into a very tight spot. Okay, so this is just with 80 modes what it will look like. And so, for instance, this atom will then have a nice polaritonic cloud around it of that virtual photon, okay, given by this wave packet. This atom is emitting a photon to a localized wave packet. Of course, all of them are doing that at the same time. And so only the particles that have their polaritonic wave packet overlapping can exchange that interaction and therefore interact. Those that are too far away cannot. So this gives one the ability to have localized local interactions and build up a graph of interactions that have some non-complete connectivity and ability for fluctuations. From a different perspective, the light that's being emitted to the cavity forms an optical lattice that's dependent on the positions. That's a fully emergent and dynamical optical lattice, in contrast to those from a single mode cavity, which is defined only by the mirror geometry. Here it's defined by the positions of the particles in a dynamical fashion. So in principle, one can have phonon-like interactions in this sort of system because it's a continuous symmetry that's broken into space. Okay, so can you do this experimentally? So we set up an experiment that looks like this, where we had a tunable amount of modes into the system. Here is just showed the TM10 and 01 modes, but we can go to full degeneracy and ask what happens to the interactions between them. So say you have just tuned it to a single mode, so there's only one TM00 mode resident near the pump in the cavity. You look at the light coming out, and you see the TM00 mode. It's more or less looks like a Gaussian. Okay, there's no surprise there. But if you tune to the fully multimode case, then what you see is a spot that comes out that's much smaller. Okay, so what's happening is that, as in the previous slide, at the position of the atoms, the modes are constructively interfering to form a wave packet that is much more localized. And so when you image that outside of the cavity, image that spot outside of the cavity at the camera position, you see a much, much tighter spot, a much more localized light field. And the width of this is simply limited by the width of the set by the Thomas Fermi radius of the BEC. So if we made it a tighter BEC, this presumably would be tighter. You can measure the two widths and show that they're the same. Okay, so that's nice. Can you show something a little bit more dramatic? So let's say that you then took the BEC, and instead of having it at the center of the cavity, you moved it up and down. What would happen? Well, first I have to tell you a little bit about confocal cavity. So the confocal cavity actually always has two spots of light coming out, because the symmetry of the resonance is always this hourglass pattern. It's because it only keeps even or odd modes. So there's always good parity across the axis of the cavity. So you would have, in other words, a virtual image or virtual BEC at this other point here, even though there's no atoms. You can think of this like in like a Jackson problem, where you have a mirror here, and these are the virtual dipoles emitting that light. Okay, it's the same kind of situation. All right, so as you do that and you move this back and forth, you see this movie of the atoms going back and forth, of one real clump of atoms and one virtual clump of atoms. And as you move them back and forth, the spot size does not change position. That shows that you have enough modes in the cavity so that even if you move the atoms far along the side, they can still constructively interfere to give you a localized spot. And then we can even move this way out here. I don't have the data to show you here, but it's in our paper. Okay? So if you have another BEC, so let's put two of them, what do you get? Well, you get this nice little dance pattern where these stripes are actually from GUI phase interactions. So I won't mention that more now, but we understand what these stripes are. And you can move them back and forth where this particle where this clump can overlap with the virtual image of this real particle and this vertical image. Okay? So it's a really nice way to actually overlap clumps of atoms with one another without physically overlapping atoms, which would suffer from actually contact interactions. Okay, so you can do this virtually. So let's do that. So now let's overlap the virtual image with the real image, and we've done this with one clump of atoms and two clumps of atoms. I'm just going to show you the data with one clump of atoms because they look identical, more or less. And we can do this for 5 different cavities with different lengths of cavities, where this is the most degenerate, and this is like in our supermode degenerate, supermode density wave polariton condensate case. This epsilon here is just the kind of measure of the splitting of these modes from each other, and the delta naught is the pump frequency. Okay, so when we do this, we get this. We measured the threshold power. So how much pump power do we need to put in order for the system to show superradiance and Bragg organization, Bragg peaks of the atomic organization? We do this as a function of the separation between these two BECs normalized to the waist of the TM00. So this is already further out than a TM00 mode. This is out to where you have more of the higher order modes. And what you see is when the two clumps start to overlap, you get an increase of the energy. Okay, this plateau here is the self energy of the particles just in each clump with themselves, but then this is indicative of the interaction energy. It's almost a factor of 2 larger. Okay, you have the extra interaction energy. And as you do this as a function of the degeneracy, the number of modes interacting, you see that it gets sharper and sharper or shallower and shallower. And that can be measured by understanding analytically what this form should be. It's approximately equal to an exponential fall off with 1 over square root of x. And you can measure some length scale, c here, okay? And then one can plot that length, and this is just, of course, the superposition of these modes analytically gives you something that looks like this. And then you can measure that as a function of that detuning for the different cavities. And the essential point here is that you can tune this interaction length from something that is basically a waste to a factor of 10, an order of magnitude smaller, to something that is only on the few micron scale. So depending on whether your atomic system is smaller than this length scale or on the order of this length scale, you can get an infinite range interaction, this complete graph, to something that is short range. Or even if you have a very dilute gas, you can tune off the interactions if this interaction range is smaller than the mean separation. Okay, so this gives you an order of magnitude tunability, and with the atomic size tunability, you can go from infinite range to short range. So we have that crucial ingredient now to do many-body physics. Okay, so what can you do with this sort of system? So many years ago, Sarang and Paul Goldbart and I thought about what can you do with such a system if you could make it, and of course, back then, we hadn't yet made it. But what we found is that you can create an exotic type of phase transition called a Brazovskii transition in a quantum setting. So instead of having this single mode cavity second order phase transition, or generally second order phase transition, what you would have in a multimode cavity is what's called a fluctuation-induced first order transition, where you have little domains of that checkerboard pattern, but overall the domain gets hampered from being continuous, from being the same everywhere by these topological defects in textures. And and that's basically because the atoms can fluctuate from one transverse mode to another transverse mode, and that fluctuation energy is enough to drive the system from second order to first order. Okay, so it's like you nucleate these little droplets with different structure inside of them. And that's analogous when one can visualize this by drawing little stripes, where the stripes can kind of change orientation and transverse periodicity. And those stripes then can collectively mimic what happens in a soft matter classical system for which you get a smectic behavior, or wandering smectic behavior. It's called a Brazovskii transition. So we call this a superfluid smectics, because if you do this with BECs, these would be superfluid channels. And what's interesting about this sort of situation is that it mimics or simulates in some very vague but nonetheless interesting way the quantum liquid crystals that are found in high temperature superconductors like pnictides and cuprates that STM probes reveal. But here, in a system, first it's bosons, of course one can do it with fermions, a system where you can control density, you can control quench disorder, and et cetera, and try to look at the interplay, the intertwined orders of this liquid crystallinity with superfluidity and even magnetism. How many domains to show? So our recent result actually shows that this can happen by showing that the ratio of the interaction length to the size of the system, if you put it in the right units, shows that the number of domains that you would have here can increase from just 1 or 2, which wouldn't show this physics, to on the order of 50 or so. So tens of different domains. So that's really the importance of that previous work, is showing that this is possible by measuring this. Okay, so Sarang in the next talk will talk about these sorts of vestigial orders, and I hope you stay for that, obviously. Another thing that we can do, and this is the last thing I'll talk about, I don't know how we're doing on time, but yeah, we're totally fine. So the last thing I will discuss is another avenue that one can go down, which is to investigate spin glasses. So as I mentioned at the beginning of the talk, instead of looking at motional organization, we can look at the spin degree of freedom of the particles and ask, either concomitant with motion or where you quench out the motion and just look at the organization of the spins themselves, what can these tailored interactions, these photon-mediated atom-atom or spin-spin interactions provide you? And to our mind, and I'm sure you'll have other ideas out there, in our mind, the exciting thing to study is spin glass. So what are glasses? They allow me to see you. They're everyday materials, but they're not understood. They have this bizarre property that they exhibit rigidity without obvious symmetry breaking. So the glass on my face microscopically looks like a liquid, yet on the age of the universe, it is rigid. Okay, it snaps. Why does that happen? It's still kind of a mystery. Nonetheless, even though structural glasses are very, very hard to describe, spin glasses, which have some related properties, can actually be described by a simple Hamiltonian. Okay, and then one can try to analyze that Hamiltonian. So this is called the Edwards-Anderson Hamiltonian. It's an Ising Hamiltonian with the modification that the Jij coupling matrix has randomly signed plus and minus interactions. Okay, and that's sufficient to give you a spin glass. Well, it has to be random. Okay. All right. So then what's exciting about this was that it was further understood in the 70s and 80s that this simple Hamiltonian is actually a really great place to start if one is trying to look at trying to mathematically analyze neural network computation or collective computation. And so you'll see this in the neuroscience, theoretical neuroscience literature as a model for neuromorphic computing. So not only does it help you to understand this bizarre state of matter, but it also helps you maybe do something practical in terms of neuromorphic computing. So what is the order if one tries to analyze it? Well, the answer to that is extremely complicated and unknown in general. But we can write down some cartoons to give you some wrong, but some otherwise some sort of notion, hand-wavy notion of what's going on. So, so what is a paramagnet? A paramagnet is, say, you have randomly distributed spins, and the spins are just fluctuating at many time scales in orientation. Okay, so that's a paramagnet. There's no order to the system. There's no non-zero order parameter. Ferromagnet, by contrast, has an order parameter, basically the magnetization. Both an antiferromagnet and a ferromagnet would have some order parameter. For the ferromagnets, the easy one to see is the magnetization, where all the spins are, say, pointed up or down. Okay, so a cartoon of a spin glass where you have both disorder and frustration kind of looks like a static version of this, and that's totally wrong. But anyways, you can kind of it's good enough for now. Where you have randomly signed interactions, but the spins aren't moving around in their orientation. They have this kind of very, very, very long scale arrested dynamics. Okay, logarithmic in time. All right, and so again, the key ingredients here are disorder and frustration. This is a simple cartoon of geometrical frustration, in which if you have antiferromagnetic interactions all around, at least one of the sites is uncertain. So you have a large degeneracy of ground states as a function of plaquette number, how many plaquettes you have. Okay, so we, many years ago, our group, Subir Sachdev here, and then we're following it up now with Jonathan Keeling and Sarang again, have been studying theoretically studying this problem of a quantum optical version of a spin glass and asking what it does. So in order to get this, you have to get spin-spin interactions. And so instead of just pumping the system, you actually want to pump the system in a more clever fashion using Raman transitions. So if you pump with just one, you get an XY interaction. If you pump with two, like so, cross like so, you get an Ising interaction. And then the sign of the product of these changes because if the spins are at the same phase of the electromagnetic field in the transverse plane, say both positive, you would have a ferromagnetic interaction if, as shown here, one's positive and one's in the negative fluctuating part of this transverse mode pattern. Then you have a negative interaction, which then gives you antiferromagnetic. So the positions of the atoms allow one to control the sign of the interaction. Okay, so if you add quench disorder, randomly position the atoms with respect to these nodes, then you can get this coupling matrix, Jij, which has the atomic parameters, has the superposition of the modes, and then this is the pump field that you can make as a standing wave. And this is this with the random positions, so that the xi and the xj's have random differences, is enough to give you the correct type of frustration for a spin glass. Okay, that's what we've shown. Moreover, this sort of looks like an RKKY type of spin glass, whose interaction range can be tuned from being long range, as I showed earlier, or short range. So if it's long range, it's Edgerton-Anderson short range. Sorry, if it's a long range interaction, it's a Sherrington-Kirkpatrick infinite range spin glass, which people know is amenable to replica symmetry breaking analysis, and that's how one studies this in a very exotic mean field framework. If it's short range, then nobody really knows what the order is, and that's a mystery that we can experimentally investigate. Okay, so on the Sherrington-Kirkpatrick side of things, the infinite range, we can use this sort of system to create something useful in principle, or at least something that does a technologically relevant activity, which is a memory, but what's called an associative memory. And so you can call this a photonic associative memory, or in other words, it's for the person who came up with the idea, a Hopfield neural network. And this is also some work that Sarang and Paul and I have done, and something that I'm continuing to do with Jonathan Keeling and Surya Ganguly and Jordan Kotler at Stanford. Okay, so what does this mean, an associative memory? So normally when we think about memory in quantum physics, we think about, okay, you write some pattern into some gas, some spins or whatever, and then at some later time, you retrieve it, and that's that. That's the end of the story. An associative memory is a little bit different, and I'll explain in a moment. First, let me explain what the elements are. So in order to connect to this kind of language, we can think of the spins as neurons. Neurons are simply biologically motivated word for nonlinear elements. The optical modes are synapses. The photons are action potential spikes. The atomic positions write in the problem, and learning is atom movement. The difference, instead of saving a single memory, like a spider, you can store multiple memories at the same time, depending on the spin configuration. If you're near one of those spin configurations, it will recapture pattern complete. Okay? Or you can just write in some other type of icing model. So we think we know how to do this. So we know how to train and retrieve memories in this system. We don't know whether it's a better heuristic for solving problems in classical or quantum computing algorithms. But we think it's an exciting area to study because we can ask questions about what is a quantum neural network? What is the role of entanglement in a neural network? What do quantum fluctuations or quantum criticality do? So to conclude, with many-body cavity QED, there are many unknowns in the system. What kind of things that we can study? What can we do with it? Is it useful? Is it interesting from a fundamental standpoint? I'm glad that all of you are joining in on this. This is exciting together, and it might be worth it from a scientific and technological perspective. So with that, I will thank all of my people that I collaborate with. Here in the audience is Sarang Gopalakrishnan. We collaborate often with Jonathan Keeling and St. Andrews, who couldn't make it. And this is Surya Ganguly at Stanford, who we collaborate with. My students are here, Yuden Guo, and Ronen is here as well, Kroze. Varun is a postdoc who's in the audience. Alicia has gone on to greener pastures with Andrew at Princeton, but she is here. And we have other science that we do in our lab, and you can talk to me about our quantum Newton's cradle with dysprosium that's dipolar, or our imaging system, the Scramscope. So thank you very much.
Super, thank you. John.
So you showed this really cool thing showing the distance dependence of the interaction, and it seemed at large distances there's a self-energy that's a substantial fraction of a recoil, right? It was plotted in recoil.
Yeah, I mean, in order to have the organization, the thing that you overcome is the recoil. That's the motional scale.
So I guess what I was wondering, if you got a substantial fraction of a recoil and the interaction has some finite range, shouldn't you be able to see a change in the Thomas Fermi radius?
That's an interesting question. The length scales are, so the Thomas Fermi radius is on a length scale of many microns, tens of microns. This ordering actually happens on the half a wavelength length scale. There's some decoupling between the overall.
The range of the interaction, that shape was on the many micron length scale as well, right?
Okay. Yeah, I think that might happen if you actually had two real BCs coming together, and so you're changing the mean field energy, which determines the Thomas Fermi range. But here you have a virtual image and the real one.
But why can't the atoms inside of one BEC interact with themselves and kind of change the shape of that one BEC? Or maybe they do and we just...
Either they do and we haven't noticed, or there's a good reason why they don't. So let me think about that. Yeah, thanks. That's exactly the kind of question we want for this meeting. It's great. Yeah.
I have a question about your quantum synectic proposal. So what is the observable there? Do you actually expect to see these patterns on the output light?
Well, if we were down the road, had a quantum microscope, maybe, but it's hard to do that with a cavity. You can look at the light coming out of the cavity, and that will have signatures of this, and that the phase and the light kind of meanders around. The atoms, the Bragg peaks should have arcs, more like, if you scatter off a liquid crystal in classical physics, you'll have arc patterns, not Bragg spots, and so you should see some spreading out of those. And the eigenspectrum of the system should change. Your soft mode should come down a little bit later as a function of pumping, and so you have to put more energy in to account for the fluctuations of the system. So there's 3 ways that you can do it.
I just have a question about the spin class that you talked about. The disorder has to be binary. Is plus or minus the same value, or it could be completely random?
It could be anything, Gaussian distributed. For most of the things I said, that is not very relevant as long as it's not biased. But even if it's biased, there are results on that as well.
So what makes it different or unique from many-body localization, for instance?
Okay, so there are very interesting relations between glasses and many-body localization. The biggest difference is that a glass, spin glass or normal glass, is classical. I mean, everything I said was classical. You can add a transverse field if you want, but you don't have to. There's no entanglement that's required in the system. So, if I touch an NBL system with my finger, it goes away. But a glass I can touch and it doesn't. So they're less
There's
fragile.
an open question as to whether MBL is any different than glass.
Yeah, or a quantum glass. I think Sarang is an expert in this. He can tell you guys much better than I could.
I'm fighting for now.
Yeah, you're up here in a second or two. Yeah. All right, great.
Thanks, Ben.
Thank you.